Okay, so we're starting on chapter 4, and chapter 4 is all about atoms and elements. That's what chapter 4 is about. Okay? Now first off, we have elements. And elements are anything that is on the periodic table. If it's on the periodic table, that's an element. If it's not on the periodic table, it's not an element. Okay? And so they're pure, but they're all of the same kind of atoms, which makes them pure substances. Now, here's really the big important thing right here. You see that? Cannot be broken down into simpler compounds. That is the key important definition of what an element is. It cannot be broken down into simpler substances. A compound can. A compound, which is two or more joined together, can be broken down. It can. But that's important, okay? So don't get the two confused. Elements cannot be broken down into simpler substances, okay? And so here are some elements and their names. A lot of them come from different languages like Greek, and there's even one that comes from German, and a lot of them are English. And also some are named by named after people, such as Curium from Marie and Pierre Curie, or places like Californium, is CF. And each one has a symbol that goes with it. Now, the symbol and the name usually are together on the periodic table. And I'm going to show you a periodic table just to show you. So let me show you a periodic table here. I've got one ready to go. And this is a periodic table right here. And if you notice, we have symbols and we have names all over here. And you can see, like, for, carbon is C, and we got carbon right below it. And you have nitrogen as N, and oxygen is O. And each one of these is a symbol and a name on the periodic table. And you may notice that some of them have two letters. Okay? Some of them have two letters, like silicon is Si and chlorine is Cl. Now, when we're doing these symbols, you got to make sure that they're capitalized. First letter is capitalized if it has two letters, and if it has one, obviously it's just one, and it's capitalized. So this is a periodic table, okay, and it has the elements on it, okay, and so every one of them has a symbol or a name that goes with them, okay, and so, like I said, they represent the names of the symbols, and we have one-letter symbols and two-letter symbols. And you may be asking yourself, well, why do we need two-letter symbols? Why not everything one letter? And that's because there's only 26 letters in the alphabet, and there's over 100 elements on the periodic table. And so a lot of them are pretty easy, like carbon is C, nitrogen N, fluorine F, oxygen O. That's pretty straightforward. And even cobalt CO. And it looks like, hey, so far so good. If I know the name of it, I know the symbol. But some of them, the names do not go. Like, take a look at iron. See, iron with Fe, it comes from ferrium. That's not there's no IR. Okay, well, actually there is. It's called iridium. And lead is Pb. And if we look over here, you see potassium. You see that? Potassium, there's no K in there, but potassium is a K. I can trip people up sometimes because P is for phosphorus. Okay? And these are pretty good common elements. It's important to memorize the name with the element. Okay? Now, most of the time, you're going to have a periodic table in front of you, and it's going to have the names on it. And so, but it's good to know. It's good to know that iron is Fe. It's good to know that copper is Cu. See over here. Here's copper. All right. It's good to know. All right. Now, we got right here, and if you have a periodic table in front of you, you should be able to say, well, let's see, iodine, and you find it, and it's an I, and we know that iron is a Fe, and then we have magnesium, well, that's Mg, zinc, well, that's Zn, and nitrogen is letter N. And you ought to be able to do it as fast as I am to memorize it, because what you don't want to be in a situation where you're doing like word search. If you've ever done puzzles called word search, and I'm sure you have, um, it can be kind of hard because you're searching. And so if you already have these memorized, you don't have to necessarily have to search around on the periodic table to find it. Okay, and sure enough, I got them right. I should get them right. All right, and so we have the names of these guys, and once again, you look on the periodic table and you see you have phosphorus, aluminum. Mn is often confused with magnesium. Mn is not magnesium, it's manganese. And of course, hydrogen and potassium. You can see this manganese. It's sort of to the left in the middle of the periodic table. All right, worry about that. Don't worry about that. And let's go on to the next PowerPoint. I'm not going to hit you with too many PowerPoints. I only do PowerPoints when it just works out. There's with definitions and such. So let's take a look at this next one here. It's about the periodic table. Let's see what I need to do here. And okay, there we go. So I'm going to enable, and we'll go ahead and start the slideshow from current slide. And here's a periodic table. And there's more than 118 elements, but there is a bunch of elements. And everything from uranium on is man-made. All right. And everything from uranium on up is natural, with the exception of Tc technetium. Technetium is man-made. It's a radioactive element that's like right in the middle of the periodic table. And so there are 91, since the last naturally occurring element is uranium 92, and one of them lower is man-made. There are 91 naturally occurring elements, 91 natural. All the others are man-made. So now, what do we have to memorize on this periodic table? Pretty much, I would say, you need to know where things are. You don't need to memorize exactly where they're at, but you need to be able to look and say, well, I know where carbon is. It's over here. There it is. And, where's potassium? Oh, there it is. And if you're looking around, if you don't know where things generally are, then you'll spend a lot of time just looking. And we don't want to do that. We don't want to spend our time looking around trying to find stuff. So try to memorize the location. I would say don't worry about these guys in here. These are probably the only ones that you really shouldn't really care too much about. Same thing down here. So everything that I didn't cross off, try to familiarize yourself with the location of those elements. Okay, so periodic table is organized into groups, and that's the up and downs, and we have periods, that's the rows. And so every one of these columns is a group. That's a group. Here's a group. All right. And the period is right here. Those are the periods. Periods 1, 2, 3, 4, 5, 6, 7. Those are rows. The period is not terribly important. What matters really is the group. And you need to be able to say what group an element is a part of. Now, what makes a group important. What makes a group important, these groups like alkali metals, there's alkali metals, here's the alkali earth metals, here's the halogens and noble gases and transition elements. But what makes a group important is groups share chemical properties. And it's important because if you know how one element behaves within a group, you can say a lot about the other elements. So if you take a look at the halogens, for instance, which are these guys in here, if you take a look at the halogens, they all behave very similarly. Now, physically, they may be different. Fluorine is kind of a yellowish clear gas. Chlorine is a greenish gas. Bromine is kind of red, and iodine is purple. Fluorine and chlorine are gases. Bromine's a liquid, and iodine is a solid. So they have different physical properties, but chemically, the halogens, for instance, they're very reactive, and they react with, and they're often found with alkali metals or alkali earth metals in nature. And so, being part of the halogens group, they all behave very similarly. And the same thing with the alkali metals, they behave very similarly as well. And so that's the important part of having groups. Now, the period is just the row number, and you got to be careful with the period because a lot of times we tend to ignore the hydrogen and helium. These are period 1. All right. And that second row that starts with lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, that's the second period. And this is going to be important when we do electronic configurations, when we have to try to decide how to do the electronic configuration. Okay, so we have group numbers, and they're at the top of the periodic table. And if you look, you see like a group 1A. See, group 1A. See group 2A. And there's also 1, 2 through, and there's also these guys here, 1 through 18. Okay. Generally speaking, we use the A designations, and we won't worry too much about these guys in here. These are our Bs. Those are our transition elements. What we will worry about is groups 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, which are these guys here. We will worry about those guys, indeed. All right. And so if you ever want to know, like one sort of question that can come up on quizzes and homeworks and reading assignments is, what element is group 2 period 4? And you look across, you find group 2A, you look down and you see where they cross over with the period. So group 2A period 4 is calcium. All right. So we have what are called the representative elements, and it's just important that you know where they are and what they're called. We have the alkali metals in group 1A, we have the alkali earth metals in 2A, halogens in 7A, and noble gases in 8A. It's very important that you know where they are and what elements are in there. Okay, so there are actually common names for the elements of 3A, 4A, 5A, 6A. There are group names for those guys, but you're not responsible for knowing those. Okay, so group 1A has these elements in it. Group 2A has those elements. And, group 1A, which is the alkali metals, are very, very reactive, which means that particularly with water, if you drop them in water, they'll actually explode when they hit water. Now, the group A's, see, they're not as, group 2A's are not as reactive, but they're still shiny like all metals are, and they include these guys right here. The further you go down, the more reactive they are. So magnesium you can hold safely in your hand. Calcium, not so much, and you definitely don't want to hold strontium in your hand because it will react with the water in your skin. And then 7A is the halogens, and they are like group 1A, they are very, very reactive. And they're not found, since they're very reactive, they're not found alone in nature. But, you get them mostly from salt, reaction of salt. And halogen actually means from salt, because halo means salt, halides, and gen means from. And so that's your group 7A. And then you have the noble gases, which is all the way in group 8A. 8A is the noble gases, and they don't react at all, and are what are called monoatomic gases. Okay, monatomic means one atom, and that means they don't even react with each other. They're all gases. The noble gases in 8A are all gases, and they're monatomic gases at that. All right. And so there's one more aspect, and that's this guy right here. There's a zigzag. A lot of times it is color-coded like it is right here, and we call those metalloids. And they have characteristics that are somewhat like, they're like metals, but not very good metals. Okay. Now the thing about the periodic table is you need to know where the nonmetals are and the metals are, because when we get the naming, you have to decide whether it's a metal with a nonmetal, which will be an ionic compound, or if it's a nonmetal with a nonmetal, in which case it's a covalent compound. But if you don't know where the metals are and you don't know where the nonmetals are, then it's kind of hard to do the naming. But if you look, you'll see that most of the periodic table are metals, and just a few are nonmetals. So up and to the right over here are your nonmetals, and down and to your left, all that blue, those are all metals. And of course, we got the metalloids running down the diagonal. Now, like I said, characteristics of metals are that they're shiny, ductile. Ductile means that you can bend it and draw it into a wire. That's what ductile means. You can bend or shape. That's what ductile means. And they conduct heat and electricity very well. If you think about what's a wire, the wire that you plug into the wall, the cord on your cell phone charger, inside the plastic is metal. Usually it's copper or aluminum. And they're all solids except for mercury. Mercury's liquid at room temperature. All right. Now, nonmetals, of course, is where I showed you on the periodic table, but you can't bend them. That's what it means to be brittle. You can't bend or shape. All right. And they don't conduct electricity very well. That's what it means to be an insulator, is it does not conduct electricity. Okay. So metals, they're shiny, that you can bend them, you can shape them. Non-metals, or they're not shiny, you can't bend them, and they don't conduct electricity. Okay. Metalloids are kind of in between the different characteristics. They can conduct electricity, but not very well. And so here's a summary of some different metals and non-metals. All right. Get past that. There's some essential elements. Okay, there it is. I'm going to discard that, go on to the next one. And I think this is going to be a little bit of history here, and then we'll stop with the PowerPoints, and I'm going to go back to my sketch pad. Like I said, I don't generally do a lot of PowerPoints, except when it's kind of like there's just concepts that need summaries, because the thing about this class is that there's going to be a fair amount of math. Once we get past the definitions and naming, there's a lot of math, and usually that's what most people need help with, and that's when I'll break out the graphical tablet. Okay. So elements are composed of atoms. Matter is generally composed of atoms, and it's the smallest particle that you can have. An atom is a very, very small thing. Now, Dalton's atomic theory, which you need to know, has four points that it makes. And first off is that atoms are really small. They're super small. You can't see them directly. And elements, the atoms in an element, are all the same. And I would say not similar, but I would say the same or identical. Okay. And when you take two or more of these atoms and join them together, then you form a compound. A compound would be like H2O. You know, an element is anything on the periodic table. H2O, which is water, carbon dioxide, sodium chloride, table salt. Those are compounds, okay? Now, the fourth line down there says rearrange to form new combinations in chemical reaction. Basically, what this is saying is when we're doing chemical reactions, we're really just moving atoms around. That's all we're doing. We're just moving atoms around, and we're breaking bonds and making new bonds. But whatever we started out with, we end up with in the end, as far as the atoms, we have new compounds. Now this right here is a restatement of arranged to form new combinations. In other words, you don't create atoms, you don't destroy atoms, you just move them around. They're just moved around. Okay, that's what that means, and that's actually called the law of conservation of matter. Law of conservation of mass. Okay, so you don't gain, you don't lose, you just move things around. All right, now we have three kinds of particles that atoms are made out of. We have protons, electrons, and neutrons. Protons are positive, electrons are negative, and neutrons are, well, they have no charge. That's why they're called neutrons. And the discovery of these guys, there's a little bit of history I want to go through here. And J.J. Thomson discovered the electron. And he said, you know what? I do know that atoms are neutral. So electrons are negative. That's what that minus sign means. And he says, therefore there must be something positive to balance out that negative. And when we have a negative plus a positive, we have neutral or zero. Okay. Now, and you may say why that is. Well, if you look around, you pick up anything, it's not going to shock you. Well, most things won't. And that means that they're neutral. You see, prior to J.J. Thomson, we knew that there were positive charges and negative charges. We just didn't know what they were. Well, he found the electron and says, well, there's got to be something positive. And so what he did is he proposed a model of the atom called the plum pudding model. And the idea is that you have the electrons, he knows they're particles, and there's just like this goo. It's a goo. It's a positive goo that the electrons are embedded in, okay? Now, the upshot of this model right here is that means an atom is round and spherical, just like it's showing, but also that it has that it's solid, just like pudding. Just like pudding, it's a gooey, but it's solid. And so if you shoot something at it, you should hit something. And so Rutherford's gold foil experiment tested it, and this is how he did it. And he fired these particles through a thin layer of gold, and you see if the plum pudding model was correct, then these guys should be filled with positive goo and electron particles, and they should be hitting them pretty much no matter what. They should be bouncing off. And what happened is that most of the particles just go straight through like there's nothing there. Nothing there. I mean, it's, and I'm not exaggerating, that center dot that I just drew, that is what you would see. Every now and then you see like a little twinkle of light on this screen. of a particle that bounced off. And so what does that mean? It means that this plum pudding model cannot possibly be correct because everything comes sailing through like there's nothing there. Okay? And every now and then you bounce off of something. And that's the nucleus. Okay? And so the conclusion is that atoms are mostly empty space. And it has a small, dense nucleus in the middle that deflects the particles. Okay? And so electrons are around the nucleus. And so we get to the model that you probably are all familiar with. If you have a proton, you have electrons zipping around, protons and neutrons in the nucleus. And now you can see, you just go sailing right on through with your particles. And every now and then, one bounces off. Okay? And so protons and neutrons make up most of the mass, and then you have the electrons. Now, this table here, which is in your textbook, you need to memorize this table. You don't need to memorize the 1.07, the 07, or the 08. And this, you can say, is practically zero. Or negligible. That's what that means when we say it's practically zero for the mass. So you can just say the mass is 1, 1, and 0 for your different subatomic particles. And so for a proton, we're going to use the P plus, and for neutron, we'll use the NO. I don't ever use these guys over here. And electron, I just usually just abbreviate it just like it shows right here. Now the charge, proton has a positive charge, neutron 0, electron -1. And protons and neutrons, well, that's where the nucleus is. And then the electrons are zipping around on the outside. So you need to memorize this in the sense of, you can say proton, positive charge, mass of about 1 in the nucleus. That's how you have to memorize it. And use flashcards or whatever you need to do to be able to take care of it. So, here's a sample question here, which one do you have found outside? Well, that must be electron, positive charge, that's positive, that's a proton. And mass with no charge? There it is, neutron, no charge. The only thing that has no charge is a neutron. And so you have to memorize that table so you can be able to answer a question like that. All right, let's see, atomic number, mass number. All right, now I'm going to go back to my sketch pad. Now, when we have symbols, we're going to have mass numbers and atomic numbers. We get to the relevant page here, and you need to be able to write them out. Okay. All right. So we're going to write out atomic symbols. All right. Now, an atomic symbol looks like this. Here's the atomic symbol for something called carbon 12. And this is how we write it. If you see it, it's carbon 12. All right. Now, there are different pieces of this. First off, C stands for carbon. Okay. And this is the atomic symbol. Now, we're doing most anything, unless you're doing chapter, I forget what it is, the atomic radiation chapter. When we're in chapter 5, which will be the next one up, we'll be using atomic symbols to do our nuclear reactions. But for everything else, we don't use these numbers. We just use the letter. Okay. Now this 6 is called the atomic number. And it is the number of protons. All right, P plus. There it is. And we find this in the periodic table. So if you look at your periodic table, you will see for carbon that it looks like this. And there it is. There is your atomic number. Now, all carbons have, all carbon have 6 protons. If it has something other than 6 carbons, it's not carbon. For instance, if it has 7 protons, it's nitrogen. If it has 8 protons, it's oxygen. So all carbons have 6 protons. Okay? Now, that's what that 6 is. Now, this 12 up here, that's called the atomic mass number. All right, and it is the number of protons plus neutrons. And I'm going to write this in red because I do not want you to do this. This number right here, that's right below carbon, is not the mass number. Do not be that person. It's not used for your atomic symbol. The atomic symbol is for what's called an isotope. More on that in a little bit, but is for one particular isotope. Okay, one particular isotope, and it's definitely not 12.011. What this 12.111 represents is an average of all isotopes. That is an average. Okay. Now, an isotope is a different kind of carbon. You have several different what called isotopes. They all have the same number of protons, but different number of neutrons. And so I'm going to write down 3 isotopes up here, and here they are. For the most common isotopes for carbon, we have carbon 13 and carbon 14. And notice they all have the same 6 on them because these 3 carbons all have 6 protons. Now notice that the atomic mass number is different. That's because they have different number of protons. And so an isotope, these are all isotopes. Same atomic number, different neutrons, or different mass number. Another way of saying this is same protons, different neutrons. Okay, that means that those two in green and blue, they mean exactly the same thing. And so if we have our 3 isotopes, what we can do is we can figure out how many neutrons each has. And what I'm going to do is just go ahead and rewrite them down here for isotopes. For carbon, we have carbon 12, which is the most common. We have carbon 13, which is not very common and radioactive. And we have carbon 14, which is also not very common and radioactive. All right. And so we can try to decide, how many protons, how many neutrons, and how many electrons each one has. Now, first off, since they're carbon, all 3 of these should have 6 protons, all 3 of them. And since they're electrically neutral, in other words, there's no charge on these guys, more on that when we get into ions, which is positive ions and negative ions, by definition, these should have the same number of electrons. So we go ahead and fill these in. So all carbons have, when they're neutral, they have 6 protons, 6 electrons, no matter what. Now, the only thing that differs between these different isotopes is the number of neutrons. And how do we find the number of neutrons? We subtract the neutrons equals mass number minus atomic number. All right? Keeping in mind that mass number is not on the periodic table. All right, it's not 12.011. You're counting out protons and neutrons to get your mass number. So if I know the mass number is 12 on carbon 12, then that means that the number of neutrons would be 6 from 12, and that gives me 6. And for carbon 13, 6 from 13 is what? That is 7 neutrons. And for carbon 14, 6 from 14 gives me 8 neutrons. So if you just take the difference between the two, you can fill out this table here. Matter of fact, you can make a table where you can fill out different elements, and I believe we do this on our lab that's coming up, and you might have a name, a symbol, you may say atomic number, atomic mass number, and protons, neutrons, and electrons, and we should be able to fill out with just one piece of information what you have. And so we could say, say aluminum, and we're told that it has, let's say it has, let me pull up my periodic table here, and let's say that it has 7 neutrons. Now with this information here, I can tell you, I can fill in the entire, just with our periodic table, I can fill in the entire table here. And so if I look at my periodic table, I look and I find, I see aluminum. There's aluminum, Al, element number 13. And I also see that since it's element 13, that it must have 13 protons. Element number 13 has 13 protons. And then I say, well, you know what? What's the atomic number? That's 13. And if you have 13 protons, you must have 13 electrons. And when I looked at the periodic table, I made a note of this. It was aluminum, Al. And now the final thing for me to calculate is protons plus neutrons to get my atomic mass number, and it's 20. And so now I can do my symbol. Small number, which is the atomic number, goes on the bottom, and the atomic mass number goes on the top. And there you go. Note that this number right here, the atomic mass number, we got it by adding together the protons and neutrons. We didn't go to the periodic table for that number right there, the atomic mass number. So we can do something similar with, say, chlorine. And I'm just going to go ahead and put the symbol here. And I'm going to say chlorine's atomic symbol is 17 for this particular isotope. Let's say 17 and 37. And if you note on the periodic table, if you're looking on the periodic table, chlorine says 35.45. That's not the number that you use for anything. Okay, don't use the number underneath the element to fill out this table. And so I look in there and I see, well, that's chlorine. I look on my periodic table. Okay, and all the information we need to fill out the rest of this table is here. Because that lower number, the 17 on the chlorine 37, well, that's the atomic number. And the 37, well, that's the atomic mass number. And the atomic number in the protons, well, that's the same. And the number of electrons is the same as the number of protons, so we can fill it all out there. Only thing we didn't need to do any calculations for is how many neutrons does it have? And we subtract these two guys right here. We subtract the protons or the atomic number. Either way, it's the same thing, but you subtract the atomic number from the atomic mass number. That gives me 20 neutrons. And we can do one more. Let's do uranium-238. So we have uranium-238, which means the 238 in the name, uranium-238. The 238 means the mass number. Okay, that's what it means. The 238 means the mass number. And so that's going to end up being copied on over. Let me go ahead and copy it. So this is uranium-238. And we're just going to copy it over to the mass number. There it is. Okay, which means that it's uranium-238. I can go ahead and do the symbol because the 238 is the mass number. I look on my periodic table and I see that uranium is element number 92. So there's the symbol for uranium-238. The 238 is the mass number. That's the big number that goes on top. And 92 I get off the periodic table. And uranium is on the bottom left-hand side in that bottom row. And so now I know 92 is the atomic number. I can go ahead and fill that out. And I know that the atomic number, the protons and the electrons are all the same. And now we need to figure out how many neutrons it has. And we're going to subtract the atomic number from the atomic mass number. And we do that when we say 238 minus 92, and I get 146 neutrons. Now, that's how you do it. That's how you do it. That's how you do the atomic symbols, and that's how you're able to look at these symbols or determine the symbols to get the number of protons, get the number of electrons, get the number of neutrons, write down the symbol, and so forth, and be able to fill out that table. All right. So